share screen. Okay. Right, good. Can people see that on the screen?
Yep.
Cool. And can people see my laser if I do that?
Yep.
Looks
Great.
good to me.
Okay, then, yeah. So thanks, Sarah. And as alluded to, I'm going to be talking about connections between ZX diagrams and error correction. So this is based on a paper that I put out with Julio Magdalena and Marcus Kesselring, and I gave a talk about it at QPL. And that paper was called Floqueifying the color code. So I want this talk to be similar, but not exactly the same, because I imagine there's some people in this Zoom room that saw the talk at QPL. So I don't want to bore them with exactly the same thing. And I also don't want to step on Fernando Pastavsky's toes, because he'll be presenting his paper, one of the PsiQuantum papers, in a few weeks, I think. And he was the one that taught me this kind of stuff. So he'll do a much better job of explaining that than I will. I think today what I want to do is connect ZX diagrams, the stabilizer formalism, and then this graphical tool called Pauli webs. So let's jump in and interrupt me at any point with questions. Don't need to put your hand up or anything, just blurt out. Cool. So to set the scene, a while ago, people came up with stabilizer codes. These are maybe the most famous type of quantum error correcting code. And the high level picture that I want to give of these is that they're very static. So you have some stabilizer group and you repeatedly measure stabilizers, so elements from this group, and this preserves a certain subspace. And you just keep doing this, preserving the same subspace, keeping the stabilizer group the same, and everything remains very, very static. Then at some point, subsystem codes came along, which the high-level picture I want to give is that they've got a little bit of dynamism in them. So more precisely, you can think of these as stabilizer codes that encode some number k, logical qubits, and I only care about some number k prime of these k. So I've got k, but I only care about k prime of them, and these other guys, I'm going to let the states of these other logical qubits move around dynamically. I don't mind what state they're in. I just care about these k prime that I've got here. And then very recently, a couple of years ago, Floquet codes came along, and these kind of changed everything. So the high level picture of these is that they're completely dynamic. So in stabilizer codes and subsystem codes, I have this stabilizer group, and I want to basically keep this the same. But in Floquet codes, the object of interest is again a stabilizer group, but I don't need to just measure elements of this group. I can measure any multi-Pauli qubit operator, and this is how the code works, by repeatedly measuring multi-qubit Pauli operators. But I can measure anything at all now. It doesn't have to be something in the stabilizer group. And I can still coherently keep track of where my logical qubits are using these new ideas that Hastings and Hart put forward in their paper 2 years ago. So this sets the scene, and it looks like, from the story I've told, that Floquet codes, these very dynamic codes, are going to be a big generalization, perhaps, of stabilizer codes, which are very static. But then there was a really, really cool piece of work about a year ago from PsiQuantum that sort of pointed towards the opposite. So a paper by these guys, it's on the archive, where they took the surface code. So this is like the most famous stabilizer code of all, for those that haven't seen it before. It works by just repeatedly measuring some weight 4 multi-qubit Pauli operators, x to the 4 and z to the 4. And they just wrote a ZX diagram for this in their paper. So by the ZX diagram for this, I mean they wrote a ZX diagram that implements some weight 4 measurements, x to the 4, z to the 4, x to the 4, z to the 4, etc. And then they did the same thing for another code that was already out there in the world called the CSS honeycomb code. We don't need to know about it. We just need to know it's a Floquet code. So it's one of these new dynamic codes. And this works by repeatedly measuring some weight 2 operators. So XX, ZZ, XX, ZZ in some pattern. And what PsiQuantum did in their paper was show that if you just write the ZX diagrams for these, apply some ZX rewrite rules, and sort of tilt your head a little bit, then there's an equivalence between these two things. So this Floquet code, which we thought was part of a class of codes that maybe really generalized stabilizer codes, turned out is exactly identical in some way to the most famous stabilizer code of all. So I thought this was super, super, super cool result. And in our paper, we basically, if I rename this to something that makes a little bit more sense for the rest of the talk, if I call this the Floquetified surface code now, one view on what we did is just to do exactly the same thing, but for the sort of second most famous stabilizer code, which is called the color code. There is a little bit more to this story, but I don't really want to talk about it in this talk, but I would feel disingenuous not to mention the authors involved. So I'll flash these up on the screen here. Since the talk is recorded, you can go back and look at these if you want. But today I just want to talk about this portion of the screen. So how do you take the color code and Floquetify it to get the Floquetified color code? But first, I should probably say, like, why would you even want to bother doing this? In the PsyQuanta paper, it was kind of clear. We already knew about the surface code. We knew about this CSS honeycomb code, as it was called then, and they found a bridge between the two, which is really interesting. But in our case, there didn't already exist a Floquetified color code. This is something that we ended up at in our paper. So you could ask, why would you want to bother? And this is the small picture. Floquet codes tend to have lower measurement weights than stabilizer codes. By this, I mean the multi-qubit Pauli operators that you measure to implement the code tend to have lower weight. So in our case, the color code has measurement weight 6, but the Floquetified color code that we find has measurement weights 2. And this is good from a quantum error correction perspective, because the higher your weights, the more chance noise has to get into your system, and the worse your code is going to perform. So this is good. There's no hard and fast rule about this, but the Floquet codes that we know of tend to have this property. The really interesting property that's not properly been well developed yet is that Floquet codes can sort of implement Clifford operators for free. So I could talk more about this at the end, because it is interesting, but the analogy would be with transversal Clifford gates in a stabilizer code. So for those that don't know, a transversal gate, we can just think of it for this slide as being a logical gate that's particularly easy to implement. If stuff isn't easy to implement, you have to do strange things like lattice surgery or braid twisting, if these buzzwords mean anything to people. You can think of transversal Clifford gates as ones that are really easy to do in a QEC code. And Floquet codes have the property that they can implement some Clifford gates in a basically even easier fashion. You just kind of get them for free sometimes, depending on what measurements you make to implement the code. So this is a really cool property. And then finally, a Floquetified version of a code could have a different qubit connectivity to the original.
Just a clarification here.
Yeah.
When you're talking about free Clifford operators, are these the Floquetified surface code? Are these the like automorphism group?
Yeah,
operators.
Exactly.
Okay, thanks.
Yeah. So the most famous example is that the honeycomb code, which was the first Floquet code to be discovered. Every 3 time steps, it implements a logical Hadamard, basically, which was a really cool property, kind of interesting. So yeah, there's some reasons why you might want to do this, but on the other hand, the bigger picture kind of says that actually maybe this isn't so interesting. And the bigger picture is that every Clifford ZX diagram can be seen as a quantum error correcting code. So we don't need to have this formalism necessarily of a stabilizer group or a dynamic stabilizer group. We can just think of every ZX diagram, every Clifford ZX diagram, as being a quantum error correcting code. And through this prism, it's maybe not that interesting that if you take the color code, you apply some ZX rewrites, tilt your head a bit, you get a new code, because they're both Clifford ZX diagrams and they're both the same. And the way we can tell what properties a Clifford ZX diagram has as a QEC code is by looking at its detectors and logicals, which we'll define in the rest of this talk. This is what we'll be building up to. But a sneak preview at this point is an example here of a Clifford circuit. If I turn this into a Clifford ZX diagram, then detectors are highlighted edges according to some rules, which we'll come to in a minute, such that no input or output legs of the overall diagram are highlighted. And logicals are similar. They are edges highlighted according to the same rules, but now we must have at least one input edge and at least one output edge highlighted. And then you can do cool things if you take this perspective seriously and you think, okay, everything I need to know to think of this as a QEC code is detectors and logicals. You can take a known stabilizer code, for example. This is a toy example that we give in our paper. This is a stabilizer code called the 422 code, where you just measure x to the 4, z to the 4, x to the 4, z to the 4 on 4 qubits. And you can apply some ZX diagram rewrites. You can reinterpret which wires in this diagram correspond to qubits. So originally I said it was 4 qubits, but I can choose that it's 12 qubits instead with this picture I've drawn here. Don't worry if this doesn't make too much sense right now. We can talk about this more at the end. I just want to give you a flavor of what you can do. So now I can think of this as a diagram on 12 qubits. And if I straighten out each of these colored wires, which represents a single qubit, then I get this Clifford circuit here, and this fits the definition of a Floquet code. So I've taken a stabilizer code and I've ended up with a Floquet code. And because I knew the detectors and the logicals on the left-hand side in the stabilizer code, I can map all of these into detectors and logicals on the right-hand side in my Floquet code. But it's good not just for learning, like building new codes from old codes. You can just get a nicer visual understanding of existing codes using these ideas. So in the 422 code, we have detectors that look like little boxes, closed boxes, and these appear everywhere throughout my code. And logicals come in pairs and they look like this. And these basically tell me where my logical qubits are. So the 422 code has 2 and they look like this. So this gives me a good kind of graphical representation of where my logical qubits are in my code and how my code uses detectors to correct errors. So this is what you can do with this perspective. And this is just a preview I wanted to give of what we'll work up to in the talk. So are there any questions so far? Great. Then let's dive in. So in this talk, I'm going to introduce Pauli webs, which Fernando Pastelski and other people at PsiQuantum came up with, but they sort of appear in different forms in other papers as well. We're going to quickly define these, and then I will introduce the stabilizer formalism, in particular, maybe another half of the stabilizer formalism that I don't think gets talked about as much as it should. And then we'll put these together to talk about detectors and logicals. So Pauli webs, alternatively called stabilizer flow in a Google paper on the left, but Pauli webs in the paper on the right by PsiQuantum. I've also seen them called firing spiders in someone's master's thesis. I forget who, I apologize. They are highlightings of ZX diagrams according to rules, basically. I can highlight edges either green, red, or blue. And they basically correspond to Pauli gates like this. So I'm going to use a blue spider with a pi phase in this talk, but it's not a well-defined spider. It's just a gate. It only works when there's 2 legs. So I can highlight edges, any of these 3 colors. And the rule as for whether I can highlight an edge, highlighted diagram is if I replace the highlighted edges with the pi gates, then I have the same diagram as if I hadn't put any pi gates on at all. So here's 2 valid Pauli webs for this phaseless green 5-legged spider here. And the general rule is that Pauli webs form a group, and these are the generators. So I can take a phaseless green spider and I can highlight any 2 legs green, or I can highlight all legs red. And these are my generators. I can multiply these together by overlaying them on top of each other. And then a leg that's highlighted 2 colors can always be turned into a leg that's highlighted 1 color using the rules on the screen here that any 2 different colored legs fuse to become the 3rd color. And any leg that's colored the same thing twice cancels out.
Pete?
Cool?
Hi, can you hear me?
Oh, yeah.
Yeah. So your definition of the Y leg,
Yeah.
what it's defined as looks like it's directed because if I read the wire in one direction, I get Y, and in the other direction, I get Y transpose.
Yeah.
Does that matter?
No, we can think of these as being sort of completely unsigned, if you like. So it doesn't matter whether I've got minus Y or Y or.
Okay. So everything's up to a global phase here.
Yeah, exactly. Craig Gidney, in his definition, stabilizer flow, talks about signed stabilizer flow and unsigned stabilizer flow. But the Pauli Webb kind of language that PsiQuantum use doesn't. And we don't need to care about this for error correction.
Right.
Can I ask a question?
Yeah.
Why there are 5 legs? Is this related to the orientation of the surface cold patch, or is there a specific design reason for this?
Nope. Sorry, this is just an example. The ... should mean any old legs. If I said 5, I probably saw 5 legs on the screen and panicked. This applies.
Are you able to count the number of independent stabilizers based on the total number of legs here?
Yeah, it would be as many pairs of legs as you can make. So if you have n legs, it would be
and choose 2.
Yeah, but they wouldn't all be independent, would they? My fault. It would be n. You would get n independent ones and an all red one.
Thanks.
I think that's right. Someone correct me if that sounds wrong.
Yeah, it's the stabilizers of GHZ, right?
Yeah, there we go. Yeah.
Yeah, I think you'd have n stabilizers in total, or generators in total, right? Because you'd have n minus 1 from all the choices of pairs, and then 1 from the all red.
Yes, exactly. Yeah, cool. Thanks. Cool. So yes, this is the Pauli Webb, the group of Pauli Webbs admissible for this phaseless spider. But I said I'm interested in all Clifford ZX diagrams, so we have to consider other phases, multiples of pi over 2. And these are almost the same, except the all red spider, all red highlighted legs has 1 blue leg. And again, I can multiply these together to get more Pauli Webbs. So these are my generators here, the top 2 rows. And for the other remaining spiders, I have exactly the same rules as for ones we've previously seen. So pi spiders follow the same rules as 0 spiders, and vice versa for the bottom 2. So Pauli Webbs only care about phases up to pi rather than up to 2 pi, which I think we'll use later on. Cool. So you can combine them by multiplying them, overlaying them, and you can also combine Pauli Webbs sequentially or in parallel. So if I want to find out quickly what Pauli Webbs I can put on the Hadamard, I can use the fact that I know the Hadamard is made up of 3 spiders, which I've written here, and I know Pauli Webbs on these. I can compose them, but I can't compose them such that the colors don't match up. So I can't do this, but I can compose them the other way so that the colors line up. And if I unfold the definition, which I'll skip over, this just tells us that we have a Pauli Webb on the Hadamard box. Cool. So that's Pauli Webbs in a nutshell. Any more questions on Pauli Webbs? Cool. Then I'll introduce the stabilizer formalism, and then we can connect these up towards the end. So I guess most people here do know the stabilizer formalism. I gave this talk to a different group recently where this wasn't the case, but I can speed through this slide if people need. So this is like our QEC toolbox, basically, that I'll introduce here. We have some n physical qubits, say, and we're interested in the Pauli group on these, Pn, because the object of interest most of the time in QEC is some stabilizer group, S. So this is some subgroup of the Pauli group that doesn't contain -1, minus the identity. And this stabilizes some subspace of my overall Hilbert space, but I like to stick to group theory where possible. So I won't talk about linear algebra too much. The other group of interest in QEC, which gets talked about less, is if I take NS, so the normalizer of S in the Pauli group, this is any Pauli such that if I conjugate S by it, I still have S, the same stabilized group. So if I take these and then I mod by S, I get a quotient group, which is isomorphic to the Pauli group on K qubits. And I can think of these K as being my logical qubits. And these guys are like my logical X and logical Zs. I've used lowercase letters here to avoid confusion. So X1 does not mean the Pauli matrix X on physical qubit 1. X1 could be like X1 tensor Z2 tensor something else. So I have these two groups basically that I'm interested in. And for me, when I talk about a logical qubit, I basically just mean a subgroup of NS mod S that's isomorphic to P1. So I basically just take a subgroup generated by these guys, for example, or this guy and these guys. And this is what I mean when I talk about a logical qubit. So I'll stay in group theory world in this talk. Okay, and then we have the stabilizer formalism itself. And I'm going to tell you that only half of the stabilizer formalism gets talked about enough. So this is the half that we do know, that's on most quantum info courses. You have some stabilizer group, and the stabilizer formalism tells you what happens to this stabilizer group when you measure a Pauli operator or you apply a Clifford operator. And it splits into 3 cases for measurements. I either measure something that was already a stabilizer up to some plus minus 1 sign, in which case my measurement outcome is deterministic. It's 0 or 1 respectively, depending on the sign. And my stabilizer group is unchanged. I have a case 2A where I measure something that isn't in the stabilizer group, even up to sign, but it anti-commutes with one of my stabilizer generators. So we say we've measured a destabilizer a lot of the time in QEC. In which case my measurement outcome is random, and I update my stabilizer group by removing S1 and adding in this here. And the third case is that I'm measuring something that's not in the stabilizer group, but this time it doesn't commute. It doesn't anti-commute with anything. It commutes with all elements of this stabilizer group. In this case, again, I have a random outcome, but I update my stabilizer group just by adding this guy in. I don't remove S1. Okay, so most people know this. I think this is on most textbooks, but there's also the question of what happens to the other group that we care about, which doesn't get mentioned so often. So there's this group which I call the logical Pauli group, and we can also split this into 3 cases. So if I measure some P, I know that S doesn't change, so therefore NS mod S doesn't change. So this case is easy. For case 2, if I measure a destabilizer, then I update the logical Pauli group as follows. Without loss of generality, I can assume that the thing I'm measuring, P, commutes with all of my Xi, Zi coset representatives here. If not, I can pick a new representative for the coset by multiplying with S1, which P does anti-commute with. And then once I've done this, a presentation for my new logical Pauli group can be found by using the same representatives as before. But note, this isn't quite the same group because S is no longer equal to S prime. Okay, and the third case is that I measure some P that commutes with everything in my stabilizer group. In this case, again, without loss of generality, I can assume that the thing I'm measuring P is either XK or ZK, the representative from up here. And in this case, I update my logical Pauli group just by removing XK bar and ZK bar from my presentation. Cool.
Teague?
Yeah.
What are you actually measuring here? So that all makes sense when I have maximal stabilizer groups. I can think about measuring a state. So what does it mean to measure a stabilizer subspace?
I don't want to measure a stabilizer subspace. If I'm talking about measuring a Pauli operator P, this would be like doing, say, a measurement of, in the surface code, for example, like I measure X to the 4. This is some Pauli measurement. This is in case 1 in the surface code, because in the surface code, my stabilizer group is generated by X to the 4, Z to the 4 in this checkerboard pattern. But if I measured just X on a single qubit, this would put me in this case here. If I measured a column of X's, like a multi-qubit, like x to the d, where d is the column length, and this was along some column of qubits, then this would put me in this case here.
Yeah, I mean, I guess it's a question about conventions here. So
okay.
So if I have a non-maximal stabilizer group, then this describes a subspace, not a state, right?
Agreed. Yeah.
So what are these probabilities of? Are these probabilities of measuring the maximally mixed state spread across that subspace, or what?
Where are the probabilities coming from?
Outcome n is random. Probability is 50%. So
yes. Then I'm thinking of this as being, so I have some n physical qubits, and I have some stabilizer group with rank R. So if R isn't equal to n, like you say, I don't have a stabilizer. My stabilized subspace isn't a state. It's still a
space,
higher dimensional subspace. Yeah. Then my measurement outcomes are, what do I want to think of them as?
Could I interject?
Right, if you're sort of embedding the maximally mixed R qubit state into that subspace, you know, if all of your logical qubits are maximally mixed.
I think the idea is that you have some state inside the logical subspace, and then you measure whichever Pauli operator you're doing, then the outcome of that measurement will be random and will project you into some eigenspace, which won't be an eigenstate. That will be a subspace.
Whether it's random would depend on what logical state you're actually in, though. I mean, consider where S is empty, right? Yeah. Then it could be any fixed stabilizer state, and some of those would have deterministic outcomes.
But then S isn't empty, is it? Then S doesn't describe the system. If the system is in some state, but my S doesn't reflect this. Maybe, yeah. So maybe this S must exactly describe the situation that we have with the n physical qubits. Maybe I should have said this. So if I have if I have n physical qubits and they're all in the 0 state, then my S must be generated by Z1, Z2, Z3. I can't say that I have these n physical qubits all in the 0 state and I'm considering some S that has no generators.
But in that case, your NS over S will always be trivial, right?
Yeah.
So it doesn't really make sense to update the NS over S because...
Oh, I hear you. Okay. So yeah. Okay. So I like to think of these things as maybe I should say, okay, on this slide. Yeah, good point. When I say this is what I mean by a logical qubit, maybe this is terrible language from me. Maybe I should say this defines a subspace in which a qubit can live. It's not a qubit in a particular state. Does that make more sense?
Yeah, I mean these two things sort of get mushed together in the quantum error correcting literature, I think, which makes it very sometimes hard to follow if you're kind of used to thinking about states. But
yeah, you're quite right. Yeah.
But I think all of those points are true if you just think, well, what would happen if I'm a sort of a uniform mixture of the code words of that space? Then
okay.
Then all of those things about deterministic versus random outcomes would be true.
Okay. Yeah. Okay, then I'll bear that in mind for future. So yes, so I guess yes, you can think of the logical qubit as being in a maximally mixed state if I have some non-empty. If these guys are non-empty, then I have some number k qubits in a maximally mixed logical state.
May I ask a question about 2p?
Yeah.
Can I think of this as a description of a subsystem code? Because it feels like you're measuring the logical gauge operators, and then this will reduce the degree of freedom that you have for your logical space. And then you basically add that measured logical operator into your stabilizer group to make the stabilizer group larger.
Yes. Yes, you can. You can think of this as being like gauge fixing. Absolutely. If you just have a stabilizer code, you can think of this as being measuring a logical operator of the stabilizer code. Yeah, both are right.
Thanks.
Okay, thanks for these questions. Are there any more? Cool. So that's measurement of some Pauli operator P, and there's similar description of what happens when you apply a Clifford operator C. So we know what happens from QI quantum info courses for the stabilizer group S. We get S prime just by conjugating all our generators by C. And it's basically the same thing in the logical Pauli group here. We conjugate all of our representatives by C, and then that gives us our new cosets. Okay, so this was the toolbox that I flashed up on the screen for QEC. But now that we know what happens to both of these groups, as we do Pauli measurements and Clifford operators, we can think of these as being dynamic in T. So we can keep track of some ST and some logical Pauli group as we do different operations. Just check the chat. I random here, perhaps. Yeah. Let's definitely pick that discussion up at the end. I'm keen to find a common ground there. Okay. And now I want to put these together to just give a really simple example of what I mean by detector and logicals. So combining the algebra and the graphical tool that we had, Pauli webs. So we have these two groups of interest, and it would be great if these corresponded exactly to the things that we're interested in QEC. They almost do. So the things that I talked about in the intro, the logicals, these are representatives of cosets of this logical Pauli group. So X1 is a logical Pauli, and so is X1S for any S in my stabilizer group, etc. It would be cool if these guys corresponded exactly to detectors, but they don't. But what is true is that every time I measure an element of this group, I create a detector. And a detector is a set of measurements whose product is deterministic in the absence of any noise. And in the next few slides, we'll just go through a really, really simple example and get to grips with what this means. So suppose I have 2 qubits and I do a Z1, Z2 measurement and with outcome A, and I follow it with a Z1, Z2 measurement with outcome B. If we look at the stabilizer group over time, at the beginning, my stabilizer group is empty. I know nothing about what state these 2 physical qubits in. You can think of these, I think, correct me if I'm wrong, Alex, or Alex, as being in the maximally mixed state, if that makes your life easier. Then I'm going to do some Z1, Z2 measurement, and the stabilizer formalism tells me that I'm going to get a random outcome A, because Z1, Z2 wasn't already in the stabilizer group up to sign, and this is my new stabilizer group now. And I can draw a Pauli web that represents this. So if we remember the rules for Pauli webs, here I have a phaseless green spider with 2 legs highlighted green. Here I have a red one. Oh, I should have said in the earlier slides that everything holds with green and red swapped. I meant to say that, but didn't. But most people in ZX hopefully have that ingrained into their brain right now. They can swap red and green. So here I have some pi spider. It could be 0 or it could be pi, but remember these are exactly the same from a perspective of Pauli webs. So here I have a red one with all legs highlighted green, so this is valid. And again, I have a green one with a pair highlighted. So I have some Pauli web on this little diagram here that's valid, and this represents a stabilizer up to sign. So if I have any Pauli web where the output legs, at least one output leg, and none of the input legs of the diagram are highlighted, then this corresponds to a stabilizer up to psi. Then I'm going to do the next measurement, Z1, Z2 again. This time, I know I'm going to deterministically get that B is equal to A, because the stabilizer formalism tells me this. And in Pauli web notation, this looks like a closed box. So I said earlier, a detector is a Pauli web where I have none of the output legs and input legs highlighted. And this corresponds always to a detector. So in this case, the detector is this condition, B equal to A. Some errors will violate this detector. So I said a detector is a set of measurements whose product is deterministic in the absence of noise. What happens if I put some noise in? So let's suppose the environment inserts a Z1 error into our ZX diagram. Then the stabilizer formalism tells us that we update our stabilizer group by conjugating all of our generators by Z1. In this case, it does nothing, and we still get B is deterministically A at the end. If the environment had put a different error in there, X1, then we would update our stabilizer group as follows, and we would end up with an extra minus sign when we conjugate. So now we have A plus 1 here, and we will find when we come to do the next measurement that B must be equal to A plus 1 deterministically. So we violated the detector. The detector was the condition B equals A, and we violated this. The environment has inserted an error that's violated our detector. If the environment inserts multiple errors, these can cancel each other out. So if it inserts a Y2 error as well, then I find that my stabilizer group goes back to just having this A here, and I get B is equal to A again. So some errors violate detectors, and some don't. So this one here did not, this one here did, and these two together did not. Cool. So detectors are how we detect errors and then correct them in QEC. And the general rule for a Pauli web that has no input and output legs highlighted is that an odd number of pi gates of a different color to a highlighted edge is a zero diagram and therefore can't happen. So I will always, if this represents a ZZ measurement, then it will always give me the outcome such that I end up with an even number of pi gates of a different color to the highlighted edges. Cool. Any questions on that? Nope.
So that's for a detector of any shape. So I could have a big complicated one, and still this even odd thing holds, right?
Yes. Confession, this is definitely true for Clifford circuits. When I first came to this, it was through the algebraic side, through the stabilizer formalism. I haven't actually written down anywhere that this would work for any generic ZX diagram. But for a ZX diagram that's also a circuit, yes. Okay, cool. So that's what happens to ST through that process. And there's a similar thing for the logical Pauli group that we care about. So if initially our stabilizer group is generated by nothing, then this is what our logical Pauli group should look like. It is just basically the Pauli group on 2 qubits, 2 physical qubits in this case. I can find a different presentation for this group by multiplying some generators around. And there's Pauli webs that correspond to logicals, as we said. So Pauli webs where at least one output edge and at least one input edge are highlighted. In this case, the diagram is so trivial, they're the same thing. These correspond to logical representatives, like that. Now, if I perform a Z1, Z2 measurement, the stabilizer formalism, the half that doesn't get talked about so much, tells me that if I'm going to measure Z1, Z2, then it's going to remove these generators from my presentation. So this is my new logical Pauli group. And again, I have Pauli webs that correspond to these representatives here. So at least one output edge and at least one input edge are highlighted. And I can keep playing this game with the next measurement. And the stabilizer formalism tells me that nothing changes. And I have Pauli webs that correspond to these logicals. And this is everything that I need to understand this diagram as a quantum error correcting code. All I need to know is what detectors does it have? How can I detect errors? and does it have any logical qubits, or rather a subspace in which a logical qubit could live in some state. So this is the main message I want to get across. This is how one can think of a QEC code that encapsulates both stabilizer codes and Floquet codes, and also subsystem codes if you think of them as just being stabilizer codes where we don't care about some of the logical qubits. Cool. So now I can get really funky. So far we've connected Pauli webs to the algebra, but we can leave the algebra behind using the ZX
Can I ask
calculus.
another question before you move on?
Yes.
So there doesn't seem to be any relationship between the number of inputs and outputs and either N or K in this code. Is that right?
That's correct. Yeah. To start with, if like I have some number of physical qubits, then my ST initially will be empty, and my NST will be PN for the N that I drew. But yes, as I'm going through the thing, it doesn't matter. There's the relationship stops as I'm doing interesting things here, and I'm measuring things that maybe commute with things already in ST or don't. Then the size of K at the end is independent of the number of legs.
Oh, but is N the number of input wires? Is that your number of physical qubits?
Yes, sorry. N, yeah, in these drawings, which are also circuits, I have N vertical lines through the whole thing.
Is that true for all the examples you do?
Yes.
Okay. That makes sense.
But K is independent.
May I ask a question about your convention here?
Yeah.
So here it looks like you're only showing either the X type or Z type stabilizer. So are we just talking about the CSS code, or you're talking about more general stabilizer codes?
Yeah, I'm talking about more general stabilizer codes. These examples happen to be CSS codes because they're the easiest ones I could come up with.
So earlier you said every Clifford ZX diagram is a QEC code. Does that mean you find a representation of any stabilizer code using the ZX diagram?
Yes. But
so they're just not in the normal form.
Say again?
They're just not in the normal form.
Yeah, they're not in a normal form. They're just, if you tell me that this stabilizer code works by repeatedly measuring a certain generating set of Pauli operator measurements, then the ZX diagram that I use is just a drawing of those measurements happening. Yeah. Cool. So if this is everything I need to understand what this diagram looks like as a QEC code, then I can start doing funky things with it that the stabilizer formalism can't tell us about. So the first thing I can do is note that Pauli webs only care about phases up to pi. So I can remove these measurement outcomes from my diagram. I can use rules like this that says that if this is a valid Pauli web, then unfusing the spider into two spiders, I still know that this must be a valid Pauli web. So I can do this to my diagram, add bits on. I can use a similar rule to move things around, but always keeping track of the detector, the Pauli web here is my point. And I can keep moving things around, but always keep track of where the Pauli web is. And now I can think of this as some new physical system. So I can think of this as 3 physical qubits now, if I want. And I can put some pi spiders back in and think of these as being some measurements. So now I have a Clifford circuit again that I could implement on some hardware in a lab. And I know everything there is to know about this as a QEC code because I knew everything there was to know about the previous diagram. And I know how the Pauli webs have changed going from one to the other. So I know, for example, that I have a detector F is equal to B here. And I had these logicals, and I know how these deform when I change the diagram. So I still know what my logical qubit looks like in this QEC code. Okay.
Could I ask about these places where the wire sort of breaks?
Yes.
are these like single qubit Pauli measurements happening to your qubits?
Yeah.
Yeah,
That's where the word is.
yeah.
Yes, exactly.
Mhm.
Yep. Any more questions on this before I summarize and we can talk about whatever we want to talk about? Cool. Then I'll quickly recap what I've said. So it used to be that we had stabilizer codes. We generalized these to subsystem codes, then Floquet codes. And I argue that you can now think of any Clifford ZX diagram as a QEC code. Some of these Floquet codes and beyond can have some nice properties. So these free logical gates I mentioned and lower weight measurements than subsystem or stabilizer codes. And the ZX calculus can let us sort of go beyond the stabilizer formalism. So we can do operations that don't have any easy analog in the stabilizer formalism. Cool. And then so some next steps would be one, to really take this new perspective and see what we can do using this as a starting point, design new codes, for example, perhaps. Could come up with a general purpose Floqueification algorithm. So we've seen PsiQuantum took the surface code and Floqueified it. We did this for the color code. We've looked at a toy example. Could you do this for any old code? And would you want to? Is another question worth answering. So, for example, LDPC codes, people really like them, but they have high weight stabilizers, high weight measurements, and non-local connections. Could you get around this perhaps by Floqueifying one of them? It would be really nice to make this story rigorous diagrammatically. So at the minute, a lot of things are just stabilizer formalism, but put into diagram form. It might be nice to start just from a diagrammatic perspective. And finally, I gave this talk a couple of times to a couple of different groups, and this paper came up, which deserves a shout out. So I put it on at the end. I would be interested in connecting this graphical picture that we've got here to Delphos and Petznick's spacetime codes, which is the similar sort of, they have a similar story in that every Clifford circuit is a QEC code, but their approach is entirely algebraic. So I just want to connect the dots between those there. Okay, and that's everything I have prepared. So thanks very much. Happy to take questions.
So as well as, oh, sorry.
I have a lot of questions, but maybe I'll try to just ask one and then let other people ask. So when you say a ZX diagram defines a code, is it that you take a Clifford ZX diagram and also you give it time steps, so you sort of stratify it, so I can define stabilizer groups at each of those steps? Is that the sense that you mean it defines a code?
Yeah, if you want to connect it back to a circuit and the stabilizer formalism and the codes defined that way, then yes, you would have to define some time steps on
it. Your answer makes it sound like there's another alternative to
there might be. The only definition I know of a code is to connect it back to the stabilizer formalism, but I would hope you could make sense of, you could just ignore that and just say, yeah, any Clifford ZX diagram, as long as I know detectors and logicals, this is a code.
A code in the sense that this is a thing that corrects errors.
Yeah.
That's interesting.
Moving away from thinking in terms of subspaces and code spaces and whatnot, just a graphical picture.
Any more? I have, yeah. So in a lot of the literature on Floquet codes and these dynamical codes, apart from that Delphos paper that you mentioned, it tends to start off with some kind of topological code and then look at turning it into a dynamical code. And I was wondering, because I don't really know very much about this, I was wondering whether that was just because topological codes are easier to reason about and you have lots of nice symmetries and all that kind of stuff, or whether you think that there's some more. Well, I guess the point of the talk is that there's no reason to strictly limit yourself to that, but like perhaps do you think that for some more general LDPC code or something, it's a lot harder to find kind of this switching between subspaces or whatever in the stabilizer formalism, and that looking at it purely diagrammatically can help kind of move away from that kind of restricted formalism?
Yeah, for sure. So yes, definitely. You don't need topological codes as a starting point to talk about Floquet codes, like you point out with the other paper as well. You can define them very generally just using the stabilizer formalism. And yes, I would also hope that thinking along these lines, either graphically or just non-topologically, just in terms of some stabilizer formalism algebra, you would have more hope of getting somewhere with Floqueifying an LDPC code.
And as a follow-up, the methods which they use to Floqueify topological codes, do you think that there's some kind of algorithmic way or methodological way to do this for, say, LDPC codes, or is it a kind of matter of shooting in the dark?
No, I think this is definitely plausible. It is something that I do want to do. I just don't know when. I would be happy if someone else wanted to do it and I could help. But yes, it is definitely something I think is worth exploring. I should say I don't know that I think some people are really like pro Floquet code. I think they're cool and they're interesting because we've expanded our definition of what it means to be a QEC code, but I don't necessarily think we should just start Floqueifying everything. Like some of the advantages that they have are trade-offs rather than outright pros. Like the fact that you have lower weight measurements is a trade-off between the weight of your measurements and the number of measurements included in any single detector. And the fact that you can do these free Clifford operators, logical operators, is cool, but it's not that much of an advantage over being able to do transversal Cliffords. And some ways of compiling circuits down, you just skip Cliffords altogether. Like if you're doing Pauli-based computation, for if that means anything to anyone, you just have a bunch of non-Clifford multi-qubit operations, and then you do a bunch of Pauli measurements at the end. So you don't ever do any Clifford operators. So it would be cool to see if you could do an LDPC code and Floqueify it such that you maybe get rid of the non-localness, but I don't know if that's possible. There might be some no-goes around that.
I was thinking, this is my last thing before I hand it over to Michael, because I see he's got his hand up for a while.
Yes,
I was thinking you could have some dynamical section of your computation which enables you to do the free the kind of automorphism group type free operators, and then you hand it over to then you stay in some consistent subspace for a while, which lets you do transversal things. And the thing about doing the Pauli product measurement type thing is that this is actually quite hard to do for a lot of LDPC codes while retaining all of the, say, asymptotic qualities that you might want, because the Pauli product measurements require you to do, or at least the only way that we know how to do them so far requires you to do something which is quite similar to the surface code using like hypergraph products.
Right.
So you're kind of limited by the asymptotics of hypergraph products if you're going to do that. So actually working out what kind of operations you can do with more general LDPC codes while keeping the good qualities of them is really tricky. And if you have to sacrifice the number of measurements you do in exchange for being able to get free operators to go with it, I think that would actually be a very powerful tool to be able to use.
That's cool. Yeah, I'd only thought about the advantages in terms of getting rid of non-locality and reducing measurement weight. I didn't think in terms of being able to do Clifford operators, because yes, people don't know how to do that so well on LDPC code. Yeah, cool. Good point. Thank you.
Okay, so from a high-level question, I'll go down to a low level because that's where I am right now. So this is just kind of going to the question of this perspective shift of viewing every Clifford ZX diagram as a QEC code. How far down does that go? As in, like, for instance, if you wanted to communicate sort of ZX for the first time, like, how would one think of the basic spiders of ZX for ZX diagrams as QEC codes unto themselves? I would think that basically the different Pauli webs that one draws there have some, easy interpretation there, but I'm not entirely sophisticated enough to know what those are off the top of my head. Okay,
so if I understand right, and correct me if I'm wrong, it might take me a second to understand exactly what you mean. So I have some ZX spiders. This is like the generator of the ZX calculus. And are you saying, what's this as a QEC code? If I'm telling you, okay, yeah, then so this would have no detectors. So it can't detect any errors. And it does have some logicals, some Pauli webs like this, that include at least one output edge and at least one input edge. And a bunch of these would be the same up to multiplying by stabilizers, which are Pauli webs that look like this, where only output edges are highlighted, at least one of them, and no input edge. So I would think of this as a rubbish QEC code because it detects no errors. But if I start plugging them together, then I can create little Pauli web bubbles, little detectors, and I can correct some stuff.
Yeah, I start to wonder on that because, of course, at the very basic level, like if I have one spider with one leg going in, that's basically like a repetition code. And so I would kind of wonder if that's a good way to, just bring people into the concept.
Yeah, okay. So if you have a spider with one leg.
One leg and several outputs.
Spider with one leg and several outputs.
I mean, that would be an encoder for a...
Yeah, that's what I mean.
For a repetition code. But I think that the formalism which in Teague's description, a repetition code would be n input qubits and then one green spider, or maybe, wait, hang on, is that right? Yeah, I think there would be one green spider and then a bunch of output legs, n output legs, because then you'd have all of the input parities would be checked.
Yeah, this is here's how I would draw a repetition code. And you could simplify this. You could merge the spiders together, like Alex says. Yeah.
Okay, thank you.
Cool.
May I follow up on Alex's question to Teague? So Alex, you just mentioned about the Pauli product measurements, and I recall in PsiQuantum's paper they had this like Pauli product measurements and Pauli product rotations to realize fault-tolerant T gates or CCZ gates. Is that what you meant? Like, I didn't understand why you connect the Pauli product measurements to using the ZX diagram to do the untopological quantum error correcting codes. I didn't see the connection here.
Yeah, sorry. To clarify the Pauli product measurements, you can, any circuit, let's say unitary circuit, you can rewrite as being a sequence of Pauli product rotations, and then rather than doing these as rotations, you can modify it so that you're doing Pauli product measurements instead. which is outlined in, I think, Latinsky's Game of Surface Codes paper is a really classic example of this. And the reason why I was connecting this to Teague's work isn't because the Pauli product measurements themselves show up in the ZX diagram description he gave explicitly, but because this Pauli product measurement way of doing logical operators is extremely common when you're dealing with surface codes and similar codes like tensor product codes and stuff like that. But if it's possible to doing the whole thing of viewing any code as being described by a Clifford ZX diagram or any stabilizer code, the idea is that rather than doing these Pauli product measurements, which to the best of our knowledge require you to have hypergraph product codes or things that are like surface codes, you could instead develop it kind of top down purely as ZX diagrams, which maybe you wouldn't be doing Pauli product measurements. You would be doing some other kind of thing, some other kind of operators, but that is actually a useful thing to be able to do because of the restriction that we have on being able to do Pauli product measurements for generic codes. Does that make sense?
So you're using the Pauli product measurements to perform the logical operations for any quantum error correcting codes?
So in principle, you can do this. The problem is that there's a paper called Low Overhead. Wait, it's a long title, so I'll just link it in chat when I finish speaking. So the idea is that for any CSS code, at least, you can perform Pauli product measurements to do your computation at the logical level. But the problem is that this requires ancilla codes which actually do the measurements. You initialize them and then measure them out in the same time step. And these ancilla codes which you initialize and then measure out, the only way that we know how to do this while keeping all of the properties of the error correcting code, like the distance and so on, is for these ancilla patches to be hypergraph product codes. And hypergraph product codes have a limit in, well, actually, the ones that the ancilla patches that you use have both vanishing rate and distance, which scales as the square root of the number of qubits, which means that if you're trying to do something more fancy with an LDPC code which has significantly better asymptotics, this really bottlenecks your computation, either in terms of the number of these logical measurements that you can do at one time, or just it might mean that the ancilla patches will dominate the scaling of your code asymptotically, which is really not good if you're looking at very fancy codes. So if you are to abandon doing Pauli product measurements as the method of computation and instead do other sorts of gates or ZX diagrams or whatever, then using something like this this formalism of expressing your logicals and detectors and so on as the ZX diagrams which Teague showed could be very useful if you want to do gates which you don't otherwise know how to do without inserting some big hypergraph product code into as an ancilla, which you don't want to do. Sorry, there's a lot of moving parts to what I said, because I was just connecting it to some other problem in quantum error correction.
This really helps. Thank you. Do we have any more questions? Yeah.
We're already over, so I'm happy to let everyone go. But if anyone does want to talk more, please do get in touch. I'm happy to talk or video call or anything.
Hang on, I'm just going to link the paper that I mentioned in the chat.
Nice.
Thank you.
Yeah, the point of this paper is that you can do Pauli product measurements for any generic CSS code while keeping all of the distance and everything that you want, but that the method in the paper initializes a big hypergraph. Well, it's finite at finite sizes. It's small. Asymptotically, it can get very big. The ancilla patch that you have to initialize. Anyway, this is very orthogonal to what Teague was talking about. So I'm sorry for sucking up the time.
No, good stuff.
So last call for question. Does anyone else have questions for Teague? So maybe we can call it a day. Finally, I wish to thank everyone for showing up and wish to thank Teague for this amazing talk. Thank you very much. And we will upload the recordings to Discord and YouTube.
Thanks, guys. See you all around.
Bye.
Thanks.